Good evening, Rahil. Welcome.
Good evening, sir.
Good evening. Had your dinner?
No, sir, not yet.
Okay, we'll get started now. I think previous session we had discussed till 27, right?
Yes, sir.
Till 27th question we have completed, I guess. So now we will be discussing from 28 onwards. Okay, so let's get started. Okay. So let's get started. Two capacitors of capacitance. So can you read it, Rahil? The question.
So, two capacitors of capacitance, 3 microfarad and 6 microfarad, are charged to a potential of 12 V each. They are now connected. They are now connected to each other with the positive plate of one joined to the negative plate of the other. The potential difference across each will be
Right. Right. Okay. So now what we are doing is we have two capacitors. What is the capacitance of one capacitor?
3
3
microfarad,
microfarad. And the other one, let us say it is
6 microfarad.
6 microfarad. Both of them, let's say, were connected to some battery. What was the voltage?
12 volts.
Yeah, basically. So they were charged up to 12 volts. Clear? Separately. Okay. Then after that, the battery is removed. So you are simply having a capacitor. What is the capacitance? 3 microfarad. And in the other case, what is the capacitance? 6 microfarad. Now, can you tell me what will be the charge on the first capacitor? What is the relation between charge, capacitance, and voltage? Good evening, Akila. Welcome.
Q by V.
Yeah, C is equal to Q by V or Q is equal to CD. So, capacitance is 3 microfarad. And the voltage to which it is charged is 12 volts. Therefore, what will be the charge? (36 microcoulomb). Clear? That is the charge on the first capacitor. What is the charge on the second capacitor? This is also charged. Of course, it's 6 micro into. This is also charged to 12 volts. So what will be the total charge? 72 microcoulomb. Clear, everyone?
Yes, sir.
Yes. Now, so far, how we were considering is, we were considering a charged capacitor connected to another uncharged capacitor, correct? In the previous questions. Now, this time, we are connecting a charged capacitor to another charged capacitor. This time, what is the charge on the first capacitor? 36 microcoulomb. And the charge on the other capacitor is 72 microcoulomb, correct?
52.
I'm sorry. Yes, good evening, Rebecca. Yes.
Good evening, sir.
Good evening. So you can see, so one of the capacitors, the charge is 36 and the other one it is 72. Important point to be noted in this question is, the positive plate of one is joined to the negative plate of the other. So whenever you're having two charged capacitors, right? So the plate which is connected to the positive terminal of the battery would be positively charged, and the plate which is connected to the negative terminal of the battery will be negatively charged on both the capacitors. Agreed? Now in this case, what they have told is the positive plate of one of them is connected to the negative plate of the other, right? So this is a positive plate and this is a negative plate, let us say. The positive plate is not connected to positive plate of the other capacitor. Positive plate is connected to what? Negative plate of the other capacitor. And the negative plate of one capacitor is connected to positive plate of the other. Is it clear to you?
Yes, sir.
Yes.
Yes.
Yes, sir.
What will be the difference if you see? If I connect positive plate to positive plate, negative plate to negative plate, then both the charges will get added up. The total charge will be the addition of the two charges, okay? If I'm connecting like this opposite, which means what? Positive plate I'm connecting to negative plate of the other one, and negative plate of this one I connect to a positive plate, then what will happen is the total charge will not be Q1 plus Q2, but what it will be? It will be the difference of the two charges. So the total charge in the system will be nothing but, let's say, Q2 minus Q1, or the greater one minus the smaller one I am doing. So it is 72 microcoulomb minus 36 microcoulomb. Therefore, what is the total available charge? Tell me. 36 microcoulomb. Suppose, now I'll ask you a question. Suppose the question had been, you are connecting the positive plate of one to the other positive plate, a negative plate to another negative plate. Then what do you expect the answer to be? What will be the total charge?
Uh, 72 plus 36.
72 plus 36. So it will be 108 microcoulomb. Are you clear?
Yes, sir.
Okay, good. So now we understood that the total charge available in the system is 36 microcoulomb, right? So what will happen? The moment you connect the two capacitors having different charges, then what is going to happen now? The moment they are brought in contact, what happens? Charge sharing happens, correct?
Yes, sir.
Yes. The charge sharing will happen until they both reach
Equal potential difference.
equal potential difference, exactly. So what will happen is now they both will reach some equal potential difference. Let's say that potential difference is C, VC, V common potential, we call it, right? Okay. Now, what is this capacitance? What are the two capacitors values? 3 microfarad and 6 microfarad. Three microfarad and 6 microfarad. So the two capacitors are connected in
Parallel.
parallel. So what will be the total capacitance, effective capacitance?
C1 plus C2.
C1 plus C2, so that will be 3 microfarad plus 6 microfarad. So what will be the total capacitance?
9 microfarad.
Exactly. So it will be 9 microfarad. That will be the total capacitance. And what is the common potential? Let's say it is VC. We know the total charge. What is the total charge in the system?
36 microcoulomb.
Yes, 36 microcoulomb. We just got it, right? So we got Q, we know C, we can find out the common potential. This is what is asked in the question. What is the common potential, or what is the potential difference in the plates of the two capacitors. So what is the relation between Q, VC and C effective?
Q is equals to CV.
Yes, ma'am. So the total charge is Q. So therefore, Q is equal to C effective into V, CV, right? So what is Q? 36 microcoulomb. What is effective capacitance? 9 microfarad.
9 mic.
Yes, into V. Micro and micro cancels. 36 divided by 9, what is it? 4. So the common potential is equal to 4 volts. Is it clear, everyone?
Yes, sir.
Yes, excellent. So I just reiterate it once more from the beginning, then we'll go to the next one. So we have been, I think last few sums we have been discussing about charge sharing between the capacitors, correct? Now, so far we had seen one is a charged capacitor, another is an uncharged capacitor, like that, right? But the same, both the capacitors are charged capacitors. Two capacitors of capacitance 3 microfarad and 6 microfarad are charged to a potential of 12 volt each. That's what I have written here. Okay. What would have happened? They would have been connected to battery separately and charged up to 12 volts. Then after that, the battery will be disconnected. But even though battery is disconnected, what will be there?
Voltage charge.
Charge will still be there. All right. Okay. So what is the total charge? What is the charge on the first capacitor? 36 microcoulomb. Charge on the second capacitor 72 microcoulomb because C.
72 microcoulomb.
Yes, yes, right. So 3 microfarad into 12. In this case, it will be 6 microfarad into 12. So we got the charges on each capacitor, right? Usually we connect, let's say, positive plate of one capacitor to positive plate of another capacitor, negative plate to negative plate. In such a case, we always have return, right? Total charge is nothing but the addition of the two charges on the capacitors. But here the connection is opposite, which means what? The positive plate of the capacitor is connected to negative plate of the other, and the negative plate of the capacitor is connected to positive plate of the other capacitor. When you do this, the total charge in the system becomes difference in the charges. So one is 72, another is 36. So the difference will be 72 minus 36, 36 microcoulomb. That will be the total charge in the system. Then that will start sharing, okay? Getting shared between the two capacitors. So the charge sharing will happen until the potentials become equal. So we need to find out what is the common potential. So for that, we need to find out the effective capacitance. So C effective is equal to C1 plus C2 because they're connected in parallel, because they have the common potential, same potential, right? So 3 plus 6, 9 microfarad, and the total charge is 36 microcoulomb. So common potential is going to be Q divided by C effective. 36 divided by 9, that's 4 volts. Is it clear to you?
Yes, sir.
Excellent. Now, shall we proceed to the next question?
Yes, sir.
Yes, sir. Okay. I'll just give you the question. You can try for a couple of minutes. See what is given? Two identical capacitors have the same capacitance C. One of them is charged to potential V1 and the other one is charged to potential V2, similar to the previous question. The negative ends of the capacitors are connected together. When the positive ends are also connected, what is the decrease in energy of the combined system? So here, how we are connecting it, can somebody explain? When you compare this question with the previous question, in this question, how are the plates connected? Can you tell me? Anyways, just spend about a couple of minutes on this, everybody. Then you come up with how we need to solve it. Yeah, who can explain? Yes, Rebecca, you want to try?
So there's two identical capacitors which is connected together, and then one of the charge. Like in the before question, we used to have only one common volt. Like so here we have two, like potential V1 and other is V2.
No. See here, there also.
No, I didn't get it.
Okay, no problem. Fine. Correct. Go ahead, Rebecca. Right.
No, sir. I'm not getting this.
Okay, no problem. Rahil, go ahead, Rahil. Try what you're understanding and just explain. Then we will. It's okay if you make mistake. Yeah.
Sir, so there are two identical capacitance, sir. So
Right.
both will be C, sir, and
Yes.
so there are two different potential differences, V1 and V2. So
Right.
the
That
negative.
means earlier they were charged by separate batteries.
Yes, sir. But
Okay.
this they are charged by the same batteries, but different voltage
Yes.
differences.
Yes.
So
And then the battery is disconnected.
yes, sir.
Now,
So
still, what will be retained by the capacitors?
charge, sir.
Charges. Individually, they'll have Q1 and Q2, right?
Yes, sir.
Okay. Now you are going to. They are already charged. Now you are going to connect them together, correct?
Yes, sir.
Yes, fine. Now, how are we connecting it?
Negative ends of the capacitors are connected. So from the
Together.
negative, yes,
And
sir,
the positive
negative.
ends are connected together, correct?
So in parallel, sir.
They are in parallel, no doubt about it. And they will have a common potential. That is also no questions about it.
Yes, sir.
Point is, what is it? Is it same as the previous question, or what is the difference? If it is, if there is.
So like Q minus Q2, Q2 minus Q1, here it will be Q2 plus Q1.
Excellent, Rahul. Very good. Because there we were connecting the positive terminal to a positive plate to the negative plate and vice versa, right? So that in that case, the total charge in the system will be Q1 minus Q2 or Q2 minus Q1. Here, the charge on the charges will get added up when you connect the negative to negative and positive to positive, right?
Yes, sir.
Yes. So you will find total Q. You will find common potential, correct? Then once that is done, then what we should find? Tell me, Rahil.
Sir,
Finally, what we need to find?
we need to find the decrease in energy.
Yes, decrease in energy. Do you remember from last class? We used to find out the initial energy.
Yes, sir.
Yes. Then we used to welcome Alvin. Okay. Good. Then we used to find out the final energy of the new system, correct? Then the difference will be the loss in energy, correct? We did that. We did 2-3 sums on that, correct?
Yes,
Yeah,
sir.
sir.
Yes. So same idea is going to be there. So let me do this now for you. So we have two identical capacitors. When I say identical, that means the dimensions and everything is identical, similar. So the capacitance will be same for both of them, right? Okay. Earlier, what would have happened is these would have been connected to some batteries. One would be charged up to V1, another is charged up to V2, correct? And then we must have disconnected the battery, right? But the capacitors we know will still hold the charge even if the battery is disconnected, correct? So capacitance will be C. What will be the charge on the first one? Q1 will be equal to C into V1. What about the charge on the second one? Q2 will be equal to C into V2. So these charges will be retained by the capacitor, correct? Now what we are doing is we are going to connect these two capacitors together, right? So the plate which is connected to the positive terminal of the battery would have become positively charged. The one which is connected to the negative terminal would have become negatively charged. Correct? Now what we are doing is, in contrast to what we did in the previous sum. In the previous sum, what we did was, we took the positive plate of one capacitor, went on and connected that with the negative plate of the other capacitor and vice versa. Here what we are going to do is we are going to connect the positive plate to the positive plate and the negative plate to the negative plate, right? Right? So what is the total charge in the system? What is the total charge given by? Q is equal to go ahead. Yes, sir.
Q is equal to CV square.
Q is CV square.
No.
Yes, Rahil, go ahead. What is the total charge in the system?
Q is equal to CV.
No, that's fine. Tell me in terms of Q1 and Q2.
Q1 plus Q2, sir.
Yeah, Q1 plus Q2. In the previous sum, it was Q2 minus Q1, right?
Yes, sir.
That was because we connected the positive plate to the
Negative plate.
and vice versa. Now here we are connecting the positive plate to positive plate, negative plate to negative plate. That means only the charges will get added up. Okay. So now you can say, so Q1 is nothing but already we got the expression. Q1 is what? CV1. And Q2 is nothing but
CV2.
So this is your Q. Okay. Now both of them would have reached a common potential, correct? Once this type of a connection is happening, then we know what will happen, right? There will be charge sharing between the capacitors. Because of that, what is going to happen is they both will reach to a common potential. And both these capacitors, what are the capacitances? C and C, right? So what will be the effective capacitance? What is the effective capacitance? Akila, are you there?
Sir?
Yes, ma'am. What is the effective capacitance? Were you listening?
Yes, sir.
Yes, Rebecca, tell me, Rebecca, what is the effective capacitance? You've done it many times.
Yes, sir. Like C1 plus C2.
Yeah, so that is C plus C, which is 2C.
2C.
So what is the common potential going to be, Rebecca?
For this sum, sir.
Yeah. Capacitance is C effective, charge is Q. So what will be the potential? That's what I'm asking. VC.
I guess Q by C.
Yes, right? So VC is equal to Q by C effective. What is the charge? CV1 plus CV2, or if I take C outside, it is V1 plus V2 divided by C effective is 2C. So we get the common potential in this case as V1 plus V2 divided by 2. That's going to be the common potential. All right. Now what is that we need to find out? We know all the things that are needed for solving the sum. We need to find the difference in energy, the decrease in the energy, right? Whenever this is happening, right? Whenever charge sharing is happening, we have already seen that there will be a loss in energy, right? So what is the initial energy, the first case? Originally, what would have been the energies? What would be the initial energy? Total initial energy. It will be the energy of the first capacitor plus energy of the second capacitor. What is energy given by? What is the expression for energy? Energy is stored in the capacitor.
Half into CV square.
Yes. So this will be half into C into V1 square. In this case, it will be half into C into V2 square. Therefore, your initial energy is going to be, I can take C by 2 outside. So what will we get? V1 square plus V2 square. Clear? So this is the initial energy that's going to be there in the capacitors individually, right? Now finally, what is going to be the energy? So initial energy, how much we got? C by 2 into V1 square plus V2 square. Now what is the final energy? What is the total capacitance? 2C. So it will be half CV square, half into, what is C here? 2C. What is the capacitor? What is the voltage? VC square. So you can see that half and half cancels. So it is nothing but C into VC square. What is VC square? V1 plus V2 divided by 2 the whole square. So this will become C into V1 plus V2 the whole square divided by 4. This will be the final energy of the capacitors. Now we are not asked the final energy. We are not asked the initial energy. What are we asked? Difference in the energies. Right? So we need to find out the difference in the energies. Change in the energy or the loss in energy. So initially the energy will be greater. Finally the energy would be lesser. Because whenever you do charge sharing, some amount of energy is being lost. So UI is C divided by 2 into V1 square plus V2 square minus UF. UF is nothing but C divided by 4 into V1 plus V2 the whole square. Correct? Okay. So now let's expand this and simplify. Okay. We can in fact take C by 4 outside. So what will this be? Because instead of taking 2, I have taken 4. So I should multiply by 2 in the numerator. So it will not be V1 square plus V2 square, but 2V1 square plus 2V2 square minus Here C by 4 I have taken out. So what is it? V1 plus V2 the whole square. V1 plus V2 the whole square. Okay. Can you simplify and tell me the answer? This becomes C by 4 into. Tell me what is going to be the answer. This will be V1 square plus V2 square plus 2V1 V2 so this will be equal to C by 4 into 2V1 square minus V1 square is 1V1 square, 2V2 square minus V2 square is 1V2 square, then plus into minus is minus 2V1 V2. So this will be nothing but A square plus B square minus 2AB. V1 minus V2 the whole square. So delta U is equal to C divided by 4 into V1 minus V2 the whole square. This is going to be a expression for decrease in energy. So which answer is correct? It will be the third option. Okay.
Third option.
Yes. Now I'm going to give you some time for taking down both the questions. Okay. Let's now look at the next question. As you can see, the next question is, you have two spherical capacitors. A and B are two spherical capacitors having charges 2 microcoulomb and 4 microcoulomb, and the capacitances are 1 microfarad and 2 microfarad respectively. The capacitors are placed at large distance from each other. When they are joined by a conducting wire, what will be the final charges on A and B? Okay. Now two spherical capacitors, right? One spherical capacitor, another spherical capacitor. So let's say this is spherical capacitor A and this is spherical capacitor B, okay? What is the charge on the spherical capacitor A? Let's say 2 microcoulomb. So the charge on A is 2 microcoulomb. And the charge on B is equal to 4 microcoulomb. And capacitance. Capacitance of A is given to be 1 microfarad. Capacitance of B is given to be 2 microfarad, all right? Now, what you're doing is you're going to just kind of connect them by a conducting wire. When you're going to connect them together, what is going to happen is, when two capacitors are going to be connected, there is going to be a process called charge sharing. This charge sharing will start whenever there is a potential difference between the two of them. When it will stop? When they both reach the same potential, correct? Now see here, after all this sharing has happened, what is going to be the final charge on A and final charge on B? That is the question, correct? Okay. Now before that, let's do one thing. Let's find out what is the potential on the capacitor A, spherical capacitor A. What is the potential on the spherical capacitor B? Let's find out. What is V? You know, Q is equal to CV, whether it's spherical capacitor or parallel plate capacitor, doesn't matter. Q equal to CV volts. So V will be nothing but Q divided by C. So can you tell me what is Q divided by C? So it is going to be 2 volts, correct? What is the charge on the first one? 2 microcoulomb. What is the capacitance of the first one? 1 microfarad.
1 microfarad.
Yes. Now we need to find out the potential. What is the formula for potential?
Q by C.
Q by C. Charge on the capacitor A divided by capacitance of capacitor A, which is 2 micro divided by 1 micro. So how much are you getting?
2, sir.
2 volts. Let's find out what is the potential on the capacitor 2. So what is that? That is going to be QB divided by CB. What is QB equal to? 4 microcoulomb. What is CB equal to? 2 microfarad. What is the voltage here? 2 volts. So both the capacitors already are at same voltage, correct or not?
Yes, sir.
Yes,
Yes.
sir.
So now when you connect it by a wire, when the charge flow will happen? Only if they have a difference in the potential, correct? As far as spherical capacitors are concerned. Now, is there any difference in the potential between the two?
No, sir.
No. Therefore, what will happen? Actually, there will be no charge sharing which will happen. The charge will not flow from one to other. Why it will not flow? Because already the potentials are
Same.
same. Clear? But this is not the case with parallel plate capacitor, correct? In parallel plate capacitors, if one capacitor is 12 volts, another is 12 volts, and they are disconnected from the battery, then what is important is you can only find a charge on each of them, Q1 and Q2. Then when you connect them, then obviously the moment the charges are going to be different, then what will happen is your charge sharing will start happening in parallel plate capacitor until they reach common potential. Here, you can individually identify what is the potential. Clear? And once the potentials are same, then no charge can flow from one sphere to another sphere. Is it clear?
Yes, sir.
So what is the answer going to be? Even after connecting by a conducting wire, the final charges will also be what? Same as what it was before. Initially, it was 2 microcoulomb and 4 microcoulomb. Now also it will be 2 microcoulomb and 4 microcoulomb. Have you understood?
Yes, sir.
Yes. Okay. You can take it down. Just a moment. I think this is clear to you. So I also mentioned the expression for capacitance of a spherical capacitor and what is the expression for voltage or potential at a point on the surface of the spherical capacitor. Fine. So now let's go ahead and look at the next question. So next question, we are coming to dielectrics, right? So dielectrics we had already seen. We will just have a small review and then we'll do the questions. So dielectrics are nothing but non-conductors of electricity. Whenever these are introduced into a capacitor between a parallel plates of the capacitor, the capacity to hold more charges is going to be there. So if it is air filled, that means there is nothing in between, right? Then capacitance of an air filled capacitor is given by epsilon naught A divided by D. Do you remember this?
Yes, sir.
Yes. Now, suppose if I am going to fill it with a dielectric medium, right? Dimensions are same, but completely I am going to fill it. The complete region is going to be filled with a dielectric like mica, water, or wood, whatever it is, right? Then the capacitance, when dielectric is present completely, right? Or I can call it as capacitance in the medium of a dielectric is given by epsilon naught A divided by D is there. Apart from that, you will multiply by a factor K. K is called dielectric constant, or it is also called relative permittivity. Okay. So this is capacitance in air being the medium between the plates, but in the second case, it is the dielectric, completely filled with the dielectric. Clear? So you will be multiplying it by a factor K. And K is different for different materials, depends on the material, correct? So what is K called? Dielectric constant, or you can call it as relative permittivity. No unit for it, it's a ratio. You will express it as epsilon R. Either epsilon R or K you can use. Fine. So you want to note it down, please note it down. If you're done, just let me know.
Done, sir.
Done, right? Okay. Now there is another case which arises, right? When the medium in between the plates is not completely filled with dielectric, but partially filled with dielectric, let us say. Let's say it is filled with a dielectric material of dielectric constant K for a distance of T, let us say. Whereas the total distance here is D. Let D be the distance of the two plates, but the thickness of the dielectric material is not completely occupying the space, but occupying partially, right? Let's say T. Then the remaining position is what? D minus T, correct? So how you can get the expression? Very simple. Or I will just give the expression for you. Derivation, we have done it previously, right? So capacitance in this case, right? Where dielectric is present, but not completely, but it is present up to a thickness of T. Then capacitance is given by epsilon naught into A divided by D minus T plus T divided by epsilon R or K. This will be the expression that we need to use when the dielectric is not occupying the whole space, but it is occupying only some small space. Is it clear? Okay. So have you noted it down?
Yes, sir.
Yes. Okay. Then fourth case is you're not having a dielectric, but you're having a metal. Conducting material. Okay. conductor you're having, or I can say conductor, conducting sheet or conducting material. In between the capacitor plates. Okay. In such a case, let's see what will happen. Suppose I have a this is a metal. Okay. Let's say this total distance is D. The small distance is, let's say, B. Okay. Now what happens is very simple. In the region of metal, where metal is there, you know, inside a metal, electric field will be 0. Yes, inside a shell, what is the inside a conducting shell? What is the electric field? 0, right? You must have learned, right? When, especially when lightning is happening, is it safer to be inside your car, or is it safer to be below a tree?
Below tree.
No, it's safer to be inside your car. Why is it so? Because your car is made of metallic body, right?
Yes, sir.
So what will happen is all the charges will be there, will be on the surface only, and then it will flow to the ground. But what happens is inside the electric field will be 0. We would have learned, right? You know, the spherical shell is there, charged conducting spherical shell is there. Gauss's law will apply in 3 cases. We will see. Do you remember?
Yes, sir.
Inside the shell, on the shell, and outside the shell. Correct?
Yes, sir.
Inside the shell, what is the expression for electric field we will get?
Is 0.
0, right? So same concept applies there. Here also the same thing applies. So inside the metal portion, the electric field is going to be 0. So only the remaining part of the capacitor, how much is the remaining portion? D minus B. Only that portion is going to contribute to the capacitance. Therefore, the formula becomes very simple. So the formula is nothing but epsilon naught A divided by simply D minus B. That's all. This is the third case. Is it clear?
Yes, sir.
Yeah, you can make a note of it, and then we'll go to the questions.
Yes, sir.
Once you're done, please let me know, then we will start the questions. Can we proceed?
Done, sir.
Done. Okay, great. Okay, now let's look at the first question here in dielectrics. Okay, an air-filled capacitor has a capacitance of, or you can say capacity of 2 picofarad. So there is nothing inside, just the air. So in this case, what is the capacitance given by? What is the formula? Simply epsilon naught A by D. This is air-filled condition. And how much is that value given to be? 2 picofarad. Now what we are doing? The separation of the plates is doubled. That means if it was D here, how much is it now? Come on, tell me. Yes, go ahead. Separation is doubled, so 2D becomes. And the interspaces between the plates is completely filled with wax. Which is a dielectric material. Okay. Now we don't know what is the dielectric constant of this. That's what we need to find out. Okay. If the capacitance has increased now to 6 picofarad, the new capacitance is 6 picofarad. Correct? What is the new capacitance? What is the expression for capacitance when a dielectric is inserted? It is going to be epsilon naught into A. And one more factor is going to be there. What is that factor? I said K is going to be multiplied. Divided by the distance between the plates. What is the distance between the plates now? It is not D, but what is it? 2D.
2D.
Yes. So this is going to be equal to 6 picofarad, correct? So let us say this is equation 1. Let's say this is equation 2. Now I need to find out K, right? So for that I can divide 1 divided by 2. So if I do 1 divided by 2, equation 1 divided by 2, on the left hand side, what will I have? Epsilon naught A into K divided by 2D. The other one is epsilon A by D. Right side I will have 6 picofarad divided by 2 picofarad. So what will get cancelled? Epsilon naught A will get cancelled. D will get cancelled. Picofarad will get cancelled. 6 and 2 will get cancelled. We will get 6 by 2 is 3. So can you tell me what is left out? K is left here, 2 is left here. So K by 2 is equal to 3. Therefore, what is dielectric constant? K equal to 3 into 2, 6. So which option is correct? The fourth option is going to be right. Direct application of the formula. That's all. Only thing additionally they are given is the distance between the plates is also increased to double its value. So instead of placing D, I am placing 2D here. Is it clear to you?
Yes, sir.
Yes, let's take
Yes, sir.
it down. And once you're done, just let me know. Okay, now let's look at the next question. So next question says, a parallel plate capacitor of capacitance C is connected to a battery of EMF V. If a dielectric slab is completely inserted between the plates of the capacitor and the battery remains connected, then what happens to the electric field between the plates? Okay. So you have a capacitor. The capacitance of the capacitor C, and it is connected to a battery of voltage V. Okay. Okay. So what is the purpose of a battery? What it will be ensuring?
Voltage, sir.
Yes, it will ensure that the voltage between across the two terminals of the capacitor is going to be V itself. So it will maintain that potential difference. Very good. Right? Now what I'm doing is, as it is connected, as it is staying connected, I'm going to insert a dielectric slab. So let's say this is C only, okay? And because of this, there are charges, correct? So the one which is connected to positive plate will be a positive plate of the battery will be positively charged. The plate of the capacitor which is connected to the negative plate will be negatively charged. Correct? We have seen this, right? Now, because of the positive charges and the negative charges, there will be an electric field between them. Correct? Yes. So let that electric field be E between the two plates. Okay, fine. Now, if this distance is D, okay, in electrostatics, you would have learned. If this distance is D and the electric field is E, do you know what is the relationship between V, E, and D? Electric field is given by V divided by D. If you've not seen this before, please take this down. So electric field between the plates of the capacitor is going to be given by the potential difference between the plates of the capacitor divided by the distance between the two plates. Okay. Now let's see what we are doing. We have the capacitor, it's connected to the battery. The battery's voltage is still V. Correct? Now, while this is there, while the battery remains connected, right? It's given battery remains connected. Now, a dielectric slag is completely inserted. So, you're going to insert a dielectric slag. Now, whenever I insert a dielectric into a capacitor, the formula for finding capacitance changes, or is it still the same? What is the formula for capacitance of an air-filled capacitor? C is equal to, come on, answer. Yes. Akila, what is the formula for capacitance of a parallel plate capacitor when air is the medium?
Epsilon naught A by D.
Yes, epsilon naught A divided by D. Correct. Rebecca, can you tell me what will be the capacitance if you insert a dielectric of dielectric constant K?
Yes, sir. It is epsilon naught K into A divided by D.
Exactly. So, same formula, only difference will be the multiplying factor K. K will be multiplied. So, it will be increased by K times the capacitance. Excellent. So, whenever you are inserting a dielectric completely into a between the parallel plates, then the capacitance will be multiplied by K. Right? So, it's epsilon naught Ka by D. So, capacitance has increased. Correct? Okay. Now, tell me one thing, whether the voltage across this capacitor has changed or not. Here in this case, the voltage was what? V. Now, you're still connected, you have connected the battery. Yes, Rahil, can you tell me what will be the voltage across the capacitor now? Will it be same as V or will it change?
It will be the same, sir.
It will be the same. Fantastic answer. Okay, congratulations. Why will it be the same? Because it is connected to the battery and the battery's job is to maintain the potential difference same. Are you clear?
Yes, sir.
Yes, so V will remain
Yes,
same.
sir.
Now, what about the electric field? So what will happen to the electric field between the plates? What is the formula connecting your electric field? E is equal to V divided by D. Has the distance changed? Has the distance between the plates changed, or is it same? Distance is same, correct? Only the capacitance has increased, right? Distance is same. What about V? V is also same. So V is same, D is same. Therefore, E will remain same. The question is about the electric field between the plates. So what do you expect electric field between the plates to be? Same. So the right answer
Same.
is third option. Are you clear?
Yes, sir.
Yes.
Yeah, sir.
Please take it down. After you take it down, I'll tell you a couple of additional concepts in this question. Now I'm going to give you additional concept in this in this question, right? So different types of questions can be asked in this type. Okay. So listen to this. So we have a parallel plate capacitor. We have connected it to a battery. So the battery's work is to maintain the potential difference constant. Correct. So now in this case, can you tell me what is happening to the charge? Charge in the first case, let us say it is Q1. What is Q1 equal to? CV. Am I right? What is the charge here? What is charge here? Is it CV or CM into V? What is the capacitance in this case? It is CM, correct? So it is CM into V. So tell me whether Q1 and Q2 are same or different. Anybody? Yes, Alvin, tell me, is Q1 and Q2 same or different?
It's different, sir.
Different, obviously. So which is greater, which is lesser?
Q2 is greater, Q1 is lesser.
Fantastic. Q2 is greater, Q1 is lesser. And Q2 is how many times that of Q1?
M times?
What is M? Where is M? No, M refers to medium, that's all.
Okay.
Just look at the formula. Okay, tell me CM and C. Capacitance in the medium and capacitance.
K times great.
Yeah, so this CM is K times C, correct?
Yes, sir.
What about Q2?
Q2 is CMV, so it's K times greater than Q1.
Exactly, exactly. Very good. So Q2 is nothing but K times Q1. Exactly. Very good. So the point to be remembered is whenever you're connecting, you're making the capacitor being connected to the battery, and while it is connected to the battery, you're inserting the dielectric. Then what increases? Definitely capacitance increases, correct? Charge also increases. Both of them increase K times. But what remains same? Voltage V remains same when you are still connected to the battery. And because V is same, E is also remaining same. All right. So they may give you a question, when the battery is connected, which of the quantities remain same, which quantities change, correct? So you must be in a position to answer them correctly. So whenever the battery is connected, intact, and at that time you are inserting the dielectric, obviously capacitance will increase K times, charge will increase K times, but potential difference remains the same. Are you clear?
Yes, sir.
Yes, excellent. Let's move on to the next question. Okay. Capacitance of a parallel plate capacitor becomes 4 by 3 times its original value if a dielectric slab of thickness T is equal to D by 2 is inserted between the two plates. What will be the dielectric constant of the slab? So this is direct application of the formula. Okay. So original value of a capacitor, which is nothing but when air is filled. So what is the capacitance of an air-filled capacitor? Epsilon naught A divided by D. Now, you have this capacitor, but you are inserting a dielectric slab. Dielectric slab this time is occupying the entire space or only limited amount of space, some space. What is the thickness of the dielectric slab you are inserting? Only D by 2, correct? Not D. So it will be like this. So you have your dielectric slab. This is D by 2. The total distance, of course, is D, correct? Now, what is asked is the dielectric constant, correct? So in this case, what is going to be the capacitance? We have already seen. What will be the capacitance in this case? Let's call it as, let this be C1, let this be C2. What is the capacitance in this case given by? It is given by, I've given you the formula epsilon naught A divided by D minus T plus T divided by K. Do you remember this? Yes?
Yes, sir.
Yes. So here, what is T equal to? T is equal to D by 2. So let's substitute that in the formula. So it's going to be epsilon naught A divided by D minus, what is T? D by 2. D is nothing but D by 2. So D by 2 into K. So what would we get? We will get epsilon naught A divided by D by 2 plus D by 2K. I can take common epsilon naught A, I can take, that's there. Denominator, I can take D by 2 common, then I will get 1 plus 1 by K. Now this will be the expression for the second capacitance. What is the first capacitance? The simple one, C1 is equal to epsilon naught A by D. Now what is given is, the second capacitance is 4 by 3 of the first capacitance. So what is given in the question is, the second capacitance is 4 by 3 times the first capacitance, right? So let's just substitute. What is C2? We got epsilon naught A divided by D by 2 into 1 plus 1 by K is equal to 4 divided by 3 into epsilon naught A divided by D. That's all. So what all will cancel? Epsilon naught will cancel, A will cancel, D will cancel. So if I just cross multiply this, 3 will come here and this whole thing will come here. So 3 will be equal to 4 divided by 2, this 2 into 1 plus 1 by K. 4 by 2 is 2. So this 2 I can bring it down. So it will be 3 by 2 is equal to 1 plus 1 by k, or in other words, 1 by k will be equal to 3 by 2 minus 1. 3 by 2 minus 1 is nothing but 3 minus 2 by 2, which is 1 by 2 is equal to 1 by k. This implies k is equal to, therefore the value of k is 2. So which is the right answer? The third option. So I'll repeat this once more for everybody. So capacitance of the parallel plate capacitor becomes 4 by 3 times of its original value if a dielectric slab of thickness d by 2 is inserted between the two plates. So what is the dielectric constant of the slab? So you can see you have a capacitor. What is the capacitance given by epsilon naught A by D? That's the original value. Now you are inserting a dielectric, not completely, but partially, up to a distance of d by 2. For that, we have a formula, right? If it is partially inserted, that means, only it occupies partial space. C2 is given by epsilon naught A by D minus T plus T by K. Here, what is the partial space it is occupying? D by 2. So I can substitute D by 2 here. So D minus D by 2 is D by 2. D by 2 plus D by 2K. You can take D by 2 outside common. You get 1 plus 1 by K. That's going to be a C2. C1 is epsilon naught A by D. In the question, it's given that the capacitance, new capacitance becomes 4 by 3 times of the original capacitance. You know that the capacitance will increase whenever you insert a dielectric, right? So capacitance will increase to 4 by 3 times the original value. So C2 is 4 by 3 times C1. So for C2, I'm substituting this 4 by 3 into C1 value, I'm substituting, cancelling, cross multiplying. So I get this 3 goes here. This 1 by 2 comes here. So 4 by 2 into 1 plus 1 by k is equal to 3. So 4 and 2 cancels 2. So 3 by 2. So 3 by 2 is equal to 1 plus 1 by k. 1 by k is 1 by 2. So that means k is equal to 2. Is it clear to everyone?
Yes, sir.
Yes, ma'am. So you can
Yes,
now
sir.
start taking it down. Just give me a minute.